Hello, everyone. As we saw in the last part of the lecture, at this point, right, Ptolemy's model had been accepted for a very long time, and Copernicus came along and proposed this heliocentric model, which, as we know now, is the correct model. But let's back up a little bit and watch a video from that basically starts at Ptolemy, but tells us a lot about the next big giant steps in the history of astronomy and in figuring out sort of the right answers for how planets orbit the sun. So remember that Copernicus basically proposed that the planets orbit in circular orbits. And we actually know that that's not true. So how did we get to that knowledge? And that's what we're going to look at in this video. Okay, this video is from the series Cosmos. So there was a series recently by Neil deGrasse Tyson that was sort of a reboot of the original series done by Carl Sagan. And if you don't know who that is, we'll probably use a few of the episodes of Cosmos here and there. But I urge you to, go on eBay or something and buy the DVDs. You can buy them from Amazon too, but it's probably cheaper from eBay. A lot of them are online, but it is a fantastic series. And I guarantee that you will enjoy every minute of it. But let's watch some of episode 3 that tells us about sort of the next steps in the history of astronomy.
When our prehistoric ancestors studied the sky after sunset, they observed that some of the stars were not fixed with respect to the constant pattern of the constellations. Instead, 5 of them moved slowly forward across the sky, then backward for a few months, then forward again, as if they couldn't quite make up their minds. We call them planets, the Greek word for wanderers. These planets presented a profound mystery. The earliest explanation was that they were living beings. How else explain their strange, looping behavior? Later, they were thought to be gods, and then disembodied astrological influences. But the real solution to this particular mystery is that the planets are worlds, that the Earth is one of them, and that they all go around the sun according to precise mathematical laws. This discovery has led directly to our modern global civilization. The merging of imagination with observation produced an exact description of the solar system. Only then could you answer the fundamental question, the one at the root of modern science. What makes it all go? 2,000 years ago, no such question would even have been asked. The prevailing view had then been formulated by Claudius Ptolemy, an Alexandrian astronomer and also the preeminent astrologer of his time. Ptolemy believed that the Earth was at the center of the universe, that the sun and the moon and the planets like Mars went around the Earth. It's the most natural idea in the world. The Earth seems steady, solid, immobile, while we can see the heavenly bodies rising and setting every day. But then, how explain the loop-the-loop motion of the planets in the sky, Mars, for example? This little machine shows Ptolemy's model. The planets were imagined to go around the Earth, attached to perfect crystal spheres, but not attached directly to the spheres, but indirectly through a kind of off-center wheel. The sphere turns, the little wheel rotates, and as seen from the Earth, Mars does its loop-the-loop. This model permitted reasonably accurate predictions of planetary motion, where a planet would be on a given day. Certainly good enough predictions for the precision of measurement in Ptolemy's time and much later. Supported by the Church through the Dark Ages, Ptolemy's model effectively prevented the advance of astronomy for 1,500 years. Finally, in 1543, a quite different explanation of the apparent motion of the planets was published by a Polish cleric named Nicholas Copernicus. Its most daring feature was the proposition that the sun, not the Earth, was at the center of the universe. The Earth was demoted to just one of the planets. The retrograde or loop-the-loop motion happens as the Earth overtakes Mars in its orbit. You can see that from the standpoint of the Earth, Mars is now going slightly backwards, and now it is going in its original direction. This Copernican model worked at least as well as Ptolemy's crystal spheres. But it annoyed an awful lot of people. The Catholic Church later put Copernicus's work on its list of forbidden books. And Martin Luther described Copernicus in these words. He said, "People give ear to an upstart astrologer. This fool wishes to reverse the entire science of astronomy." Close quote. The confrontation between the two views of the cosmos, Earth-centered and Sun-centered, reached its climax with a man who, like Ptolemy, was both an astronomer and an astrologer. He lived in a time when the human spirit was fettered and the mind chained, when angels and demons and crystal spheres were imagined up there in the skies. Science still lacked the slightest notion of physical laws underlying nature. But the brave and lonely struggle of this man was to provide the spark that ignited the modern scientific revolution. Johannes Kepler was born in Germany in 1571. He was sent to the Protestant seminary school in the provincial town of Maulbronn to be educated for the clergy. It was a strict, disciplined life, up before dawn to begin a long day of prayer and study. This was the age of the Reformation. Maulbronn was a kind of educational and ideological boot camp, training young Protestants in the use of theological weaponry against the fortress of Roman Catholicism. There was little reassurance or comfort here for a sensitive boy like Kepler. He was intelligent, and he knew it. That, together with his stubbornness and his fierce independence, served to isolate him from the other boys. Kepler made few friends in his 2 years at Maulbronn. So he kept to himself, withdrawn into the world of his own thoughts, which were often concerned with his imagined unworthiness in the eyes of God. He despaired of ever attaining salvation. But God to him was more than punishment. God was also the creative power of the universe. And the young Kepler's curiosity about God was even greater than his fear. He wanted to know God's plan for the world. He wanted to read the mind of God. This was his obsession. It was to inspire all his great achievements. It was to take him and Europe out of the cloister of medieval thought. In places like Maulbronn, the faint echoes of the genius of antiquity still reverberated. Here, in addition to theology, Kepler was exposed to Greek and Latin, music and mathematics. And it was in geometry that he thought he glimpsed the image of perfection. He was later to write, "Geometry existed before the creation. It is co-eternal with the mind of God. Geometry provided God with a model for the creation. Geometry is God himself." But the real world of Kepler's time was far from perfect. It was haunted by fear, pestilence, famine, and war. Superstition was a natural refuge for people who were powerless. Only one thing seemed certain: the stars themselves. It was remembered that in ancient times the astrologer Ptolemy and the sage Pythagoras had taught that the heavens were harmonious and changeless. And Ptolemy had said that the motions of the planets through the stars of the zodiac were portents of events here below. Was it the influence of Mars and Venus that made his father a brutal man, a mercenary who had abandoned him? Did an unfortunate conjunction of planets in an adverse sign make his mother a mischievous and quarrelsome woman? If such things were fated by the stars, then perhaps there were hidden patterns underlying the unpredictable chaos of daily life. 1589, Kepler left Malvern to continue his studies at the great university in Tübingen. It was a liberation to find himself amidst the most vital intellectual currents of the time. One of his teachers revealed to him the revolutionary ideas of Copernicus. Kepler relished this urbane, scholarly community. Here, his genius was recognized at last. Kepler was not to be ordained after Tübingen. Instead, to his great surprise, he found himself summoned to Graz in Austria to become a teacher of high school mathematics. Kepler was not a very good teacher. The first year in Graz's mathematics class had only a handful of students. The second year, none. He mumbled, he digressed, he was at times utterly incomprehensible. He was distracted by an incessant clamor of speculations and associations that ran through his head. And one pleasant summer afternoon, with his students longing for the end of the lecture, he was visited by a revelation that was to alter radically the future course of astronomy and the world. There were only 6 planets known in his time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. For some time, Kepler had been wondering, why only 6 planets? Why not 20 planets or 100? And why this particular spacing between their orbits? No one had ever asked such questions before. In the course of a lecture on astrology, Kepler inscribed within the circle of the zodiac a triangle with 3 equal sides. He then noticed, quite by accident, that a smaller circle inscribed within the triangle bore the same relationship to the outer circle as did the orbit of Jupiter to the orbit of Saturn. Could a similar geometry relate the orbits of the other planets? Now Kepler remembered the perfect solids of Pythagoras. Of all the possible 3-dimensional shapes, there were 5, and only 5, whose sides were regular polygons. He believed that the 2 numbers were connected, that the reason there were only 6 planets was that there were only 5 regular solids. In these perfect solids, nested one within the other, he believed he had discovered the invisible supports for the spheres of the 6 planets. And this connection between geometry and astronomy could, he thought, admit only one explanation: the hand of God, mathematician. The intense pleasure I received from this discovery can never be told in words, he said. Now I no longer became weary at work, Days and nights I passed in mathematical labors until I could see whether my hypothesis would agree with the orbits of Copernicus or if my joy would vanish into thin air. But no matter how hard he tried, the perfect solids and the planetary orbits did not agree with each other very well. Why didn't it work? Because unfortunately, it was wrong. The true orbital sizes of the planets, we now know, have absolutely nothing to do with the 5 perfect solids, as the later discovery of Uranus, Neptune, and Pluto shows. But Kepler spent the rest of his life pursuing this geometrical phantasm. He couldn't abandon it, and he couldn't make it work. His frustration must have been enormous. Finally, he decided that it must be the long-accepted planetary observations that were inaccurate, and not his model of the nested solids. There was only one man in the world who had access to more precise observations. That man was Tycho Brahe, who, as chance would have it, had recently written Kepler to come and join him. Kepler was reluctant at first, but he had no choice. In 1598, a wave of oppression enveloped Graz. It was spearheaded by the local Archduke, who vowed to restore the Catholic faith to the province and, in his own words, would rather make a desert of the country than rule over heretics. Kepler's school was closed, people were forbidden to worship or to sing hymns or to own books of a heretical nature. Those who refused to embrace Catholicism were fined 10% of their assets and exiled from the country on pain of death. Kepler chose exile. Hypocrisy I have never learned. I am in earnest about faith. I do not play with it. For Kepler, it was only the first in a series of exiles forced upon him by religious fanatics. Now he decided to accept Tycho Brahe's open invitation. Brahe, a wealthy Danish nobleman, lived in great splendor and had recently been appointed imperial mathematician at Prague. Kepler left Graz with his wife and stepdaughter and set out on the difficult journey. Kepler's wife was not a happy woman. She was chronically ill and had recently lost 2 young children. The marriage itself was no comfort. She had no understanding of her husband's work and regarded his profession with contempt. Kepler was married to his work, and every tedious mile was bringing him closer to the great Tycho Brahe, whose observations, he devoutly hoped, would confirm his theory. Kepler envisioned Tycho's domain as a sanctuary from the evils of the time. He aspired to be a worthy colleague to the illustrious Tycho, who for 35 years had been immersed in exact measurements of a clockwork universe, ordered and precise. But Tycho's court was not at all what Kepler had expected. Tycho himself was a flamboyant figure, adorned with a gold nose. The original had been lost in a student duel fought over who is the superior mathematician. And he maintained a circus-like entourage of assistants, distant relatives, and assorted hangers-on. Kepler had no use for the endless revelry. He was impatient to see Tycho's data, but Tycho would give him only a few scraps at a time. Tycho, he said, gave me no opportunity to share in his studies. He would only, in the course of a meal, and in between other matters, mention, as if in passing, today the figure of the apogee of one planet, tomorrow the nodes of another. Kepler was ill-suited for such games, and the general climate of intrigue offended his sense of propriety. Their cruel mockery of the pious and scholarly Kepler depressed and saddened him. My opinion of Tycho is this. He's superlatively rich, but knows not how to make proper use of it. Tycho possesses the best observations. He also has collaborators. He lacks only the architect who would put all this to use. Tycho was unable to turn his observations into a coherent theory of the solar system. He knew he needed the brilliant Kepler's help. But simply to hand over his life's work to a potential rival, that was unthinkable. Tycho was the greatest observational genius of the age, and Kepler the greatest theoretician. Either man alone could not achieve the synthesis which both felt was now possible. The birth of modern science, which is the fusion of observation and theory, teetered on the precipice of their mutual distrust. The two repeatedly quarreled and were reconciled, until, a few months later, Tycho died of his habitual overindulgence in food and wine. Kepler wrote to a friend, on the last night of Tycho's gentle delirium, he repeated over and over again these words, like someone composing a poem. Let me not seem to have lived in vain. Let me not seem to have lived in vain. And he did not. Eventually, after Tycho's death, Kepler contrived to extract the observations from Tycho's reluctant family, observations of the apparent motion of Mars through the constellations obtained over a period of many years. The data from the last few decades before the invention of the telescope were by far the most precise ever obtained up to that time. Kepler worked with a kind of passionate intensity to understand Tycho's observations. What real motions of the Earth and Mars about the Sun could explain to the precision of measurement the apparent motion as seen from the Earth of Mars in the sky. And why Mars? Because Tycho had told Kepler that the apparent motion of Mars was the most difficult to reconcile with a circular orbit. After years of calculation, he believed that he had found the correct values for a Martian circular orbit which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and, of course, 90 degrees from horizon to zenith.
So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom, because 2 further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer, and months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully.
In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times.
Kepler's first 2 laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys, as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question: what makes the planets go? Kepler's third, or harmonic law, states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power. of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law. Kepler was the first person in the history of the human species to understand correctly and quantitatively how the planets move, how the solar system works.
The man who sought harmony in the cosmos was fated to live at a time of exceptional discord on Earth. Exactly 8 days after Kepler's discovery of his third law, there occurred in Prague an incident that unleashed the devastating 30 Years' War. The war's convulsions shattered the lives of millions of people. Kepler lost his wife and young son to an epidemic spread by the soldiery. His royal patron was deposed, and he was excommunicated from the Lutheran Church for his uncompromising independence on questions of belief. He was a refugee once again. The conflict, portrayed on both sides as a holy war, was more an exploitation of religious bigotry by those hungry for land and power. This war introduced organized pillage to keep armies in the field. The brutalized population of Europe stood by helpless as their plowshares and pruning hooks were literally beaten into swords and spears. Rumor and paranoia swept through the countryside, enveloping especially the powerless. Among the many scapegoats chosen were elderly women living alone who were charged with witchcraft. Kepler's mother was taken away in the middle of the night in a laundry chest. It took Kepler 6 years of unremitting effort to save her life.
In Kepler's little hometown, about 3 women were arrested, tortured, and killed as witches every year between 1615 and 1629. And Katerina Kepler was a cantankerous old woman. She engaged in disputes which annoyed the local nobility, and she sold drugs. Poor Kepler thought that he himself had contributed inadvertently to his mother's arrest. It came about because he had written one of the first works of science fiction. It was intended to explain and popularize science and was called The Somnium, the dream. He imagined a journey to the moon, with the space travelers standing on the lunar surface, looking up to see, rotating slowly above them, the lovely planet Earth.
Part of the basis for the charge of witchcraft was that, in his dream, Kepler used his mother's spells to leave the Earth. But he really believed that one day human beings would launch celestial ships with sails adapted to the breezes of heaven, filled with explorers who, he said, would not fear the vastness of space. He speculated on the mountains, valleys, craters, climate, and possible inhabitants of the moon. Before Kepler, astronomy had little connection with physical reality. But with Kepler came the idea that a physical force moves the planets in their orbits. He was the first to combine a bold imagination with precise measurements to step out into the cosmos. It changed everything.
This very good series, Cosmos, has a lot of episodes, and it, again, a lot better to watch it on a DVD because when people upload these things to YouTube, sometimes they get issues. As you saw, there was a couple times in the video where the sound tends to cut out, which is a little odd. Anyway, but as you see, after Copernicus, right, who proposed that there were circular orbits, Kepler came along and through much struggle, as you see from the video, using Tycho Brahe's great observational skill and data, figured out finally that the correct answer, which is that planets move in ellipses. So just to give you a little more background here. So Tycho Brahe, great observer of planetary positions, and this was with the naked eye. So he compiled this very, very accurate to 1 arc minute measurements of planetary positions, which is what Kepler used to figure out that circular orbits were not going to work, right? He couldn't detect stellar parallax. Now, you probably don't know what that is yet. That parallax is the apparent change in motion when you look from 2 different vantage points. So you can make parallax happen if you look at look at something in your local room or wherever you're watching this, and cover one eye and then the other, and you'll see the object changing position as you do it. That's parallax, and we observe parallax in stars because we are at one point in our orbit, right? Let's say at the winter solstice, and we're looking at stars. And then if we go to the other side of the orbit, right, at the summer solstice, we're looking from a different vantage point. And in fact, we can detect the changes in the apparent position of stars. And that tells us a lot about how far away they are, etc. And he still really thought of Earth as the center of the solar system, but recognized that other planets go around the sun. So that's kind of an interesting dichotomy there, right? That he thought of the Earth as the center, but that other planets orbited the sun. So a little funny there. And then he hired Kepler, as you saw in the video, because he really wanted to understand this, and he was really the observational person, great talent there, but could not get the theoretical mathematics needed to understand it. So he hired Kepler. And I think the most amazing thing about Kepler is what a true scientist he really was. So, I mean, I think one of the hallmarks of being a scientist is sort of fearlessness in the face of data that doesn't match your theory. So remember, he tried to match Tycho's observations using circular orbits, but that did not work. Now, you can just imagine yourself doing something like this. At some point, if you weren't as obsessive as Kepler, and in some sense, to be a scientist means you've got to be a little bit obsessive, you may have been like, oh, forget it, right? It's only 8 arc minutes. Remember, there was this 8 arc minute discrepancy between using circles, right? And if you use circles, he had this 8 arc minute discrepancy between his calculations and Tycho's observations. You can imagine yourself having worked for years on this, just saying, well, forget it. There must be some mistake somewhere. Maybe it's Tycho's, and I'll just, never mind that, right? Because it matches mostly, right? If you remember in the video, it talked about how it matched, circular orbits matched most of Tycho's observations. So, but this sort of fearlessness in the sense that you're just not going to let that go, right? You cannot let it go. Really can lead to some really great, has led to some great discoveries. So this kind of story is not unusual in science, where there was something in the data that just you couldn't let go, even though it was small, and that leads to a whole breakthrough. And so again, Sagan quoted this in the video, but I think it's a great sort of hallmark of great science. So Kepler wrote, if I had believed that we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly, right? Because his hypothesis was circular orbits. But since it was not permissible to ignore, I'm sure he wanted to at some point, those 8 minutes pointed the road to a complete reformation in astronomy. So it's a kind of an amazing thing. Again, this is kind of a hallmark of great science. It's just not letting go of, not ignoring things when you know, It's not quite right, right? Even though it would be so convenient just to ignore it. Anyway, okay, so Sagan mentioned the three laws, Kepler's three laws, and we're going to start with the first. So his first law is that the orbit of each planet around the sun is an ellipse with the sun at one focus. So let's review what ellipses are. You might remember this from, I don't know when you study ellipses, maybe middle school. So ellipses are these things that are kind of a squashed circle, and they have two foci, so the focus is here, and another one. And the distance between the center and the outer edge here is called the semi-major axis. Okay, so let's look at a little simulation here. Just a little ellipse drawer, if I can find it, ellipse simulator, here we go. So it's really cool because you can move these foci around. So I'm going to move the foci apart. So say this is where the sun is, and here's the second focus that was empty in that picture. And the cool thing is that you can draw an ellipse for yourself, right? Get two push pins, piece of string. This is kind of like remember compasses that allow you to draw a circle? This is kind of a compass that allows you to draw an ellipse, but you could make one yourself. You could make one for a circle too, but this is just FYI, right? So if I just pull the string around, right, I keep it taut, I get an ellipse. Okay, it's like a little bit squashed circle. Notice what happens when I pull these two foci apart. I'm going to pull them really far apart. There we go. And now I'm going to erase that stuff, and let's take a look. Oh, it's kind of hard to drag around. Here we go. Right, so it's really squashed. Right? So when the foci are really far apart, it gets really squashed. And when they're really close together, here we go. Now look what happens. Erase, go away. Now that looks a whole lot like a circle, doesn't it? Let's fill it in a little bit. So even though it's actually not, right? Those two foci would have to be right on top of each other and equal in position, right? They would have to really be superimposed for this to actually be a circle, but it's pretty hard to tell it's not a circle just by looking at it, right? That's kind of how the Earth's orbit is. It looks kind of circular, but it's really not. Okay, so we'll go back to our PowerPoint. All right, so let's take another look at that. So here again is our pencil with the two tacks, right? So the distance between these two foci tells you really about how eccentric the ellipse is. So eccentricity is how we measure how squashed it is, right? How elongated and squashed it is. If you have an eccentricity of 0, notice the two foci are right on top of each other, right? So this is, you can't tell that here, but there's supposed to be two foci here right on top. That gives you an eccentricity of 0, and that is really just a circle, okay? Now, as you pull those two foci apart, you can see the pencil would trace out this little flatter thing. The farther apart they are, the more eccentric the ellipse is. This is sort of moderately eccentric and highly eccentric. Okay, so this measure of eccentricity is a number that's between 0 and 1. So if it's 0, it's a circle, and if it's 1, it's like a line. Basically, it's so squished that it's basically a line. So between 0 and 1, that number, the closer it is to 1, the eccentricity, it tells you how squashed and flat it is. So closer to 1, more squashed and flat. All right, so that's a higher eccentricity. Okay. All right, so let's try a question. All right, so which planet has a more flattened elliptical orbit? One that has an eccentricity of 0.2 or one that has an eccentricity of 0.6? So this is supposed to be for planet 1 and this is for planet 2. Well, the eccentricity is bigger for planet 2, right? Closer to 1. So it's going to be planet 2. Indeed, that's true. Okay, now it's your turn to answer a question. Don't forget to pause the video.